I know him as the author of the Asmodeus scanner for NT, which in its day was one of the fastest port scanners, or the fastest port scanner on NT. Since then, he's started a company, click2secure.com, and he's going to be talking on advanced buffer overrun techniques. I don't know if the Singapore material's online. He presented this in Singapore, and it went over really well, and since then he's refined it a bit and gotten a little bit more advanced. So the goal here is to hopefully alienate a good percentage of you with technical knowledge to the point that it forces you to go out and learn some of this. We also have Eli here, who's going to be taking questions from the audience. Most of the questions will be at the end, but if you have a pertinent question, please feel free to raise your hand and we'll get the question answered. Let me see. Any other good stuff?
Oh, no, that's good.
That's good? Okay. Oh, yeah, also check out rootkit.com. There's a lot of cool work being done there on how do you install rootkits and defend against rootkits and hide stuff in memory and find stuff in memory, so it's sort of both sides of the battle. Rootkit.com, it's what, OpenCVS is there too?
Yeah, CVS.
So there's CVS stuff there, you can download different projects, contribute to different projects. Okay. Here is Greg Hoglund.
Yeah, I'm just doing a mic check here. Okay. Thank you, Jeff. First of all, I'd like to thank Eli for saving my butt with this laptop right here. I have Windows 2000 installed on a Sony Vaio, and it does not have external video support, unfortunately. So in the last 10 minutes, we've been scrambling to get this thing over onto his laptop. So thanks, Eli, a whole lot for that. I'd also like to thank everybody else who's here, especially all my hacker friends who've been around for a couple of years now. You guys have been really supportive, and I really appreciate all the help you've given me. And lastly, I'd like to thank Jeff Moss. Black Hat is the coolest show. The technical eliteness here just oozes, and I don't think you're going to find that at any other show. If you're an admin and don't want to learn anything new, go to SANS, but if you're really, really hardcore, come to Black Hat. Okay, so my talk is Advanced Buffer Overflow Technique. There are some techniques I'm not going to actually cover in the talk that are covered in a chapter that I just recently wrote. Oh yes, thank you, Ryan Russell. Ryan Russell got this book out in an incredible amount of time. And I wrote one chapter. I had the opportunity, thanks to Ryan. There's a couple other really cool people you recognize. Rainforest Puppy, Mudge, Oliver, Caesar. This is a really good book. So anyways, Security Focus, at their booth, I think they have some. And I brought 3 copies, so I'll ask like some really insane question somewhere during the talk, and if you can answer it, I'll give you a copy. It'll be cool. What's that? The title? Oh, I'm sorry. Yeah, I'm going too fast here. Hack-proofing your network. The title changed like 10 times in the time it was being written, so I kind of stopped paying attention to that. Okay, let me get started. There's kind of 3 parts to this talk. The first one, I'm just going to kind of go over some ideas about buffer overflows. I'm mainly going to try to make the point that buffer overflows are kind of like weapons, and they have a certain amount of abstraction to them. You can have an injection part of an attack that's separated from the payload part of an attack. So it's kind of like a missile and a warhead. So I'll talk a little bit about that. Then we're going to get a little more technical and talk about injecting code. And then we're going to start talking about payloads and some of the tricks you're going to have to pull to make a payload work. This is geared towards people who program. So hopefully you're not scared of seeing some assembly language. So one of the things definitely important here is size restrictions, so we're going to focus on that too. As you get smaller and smaller payloads, obviously you're going to have to start writing tighter and tighter assembly language and pull in some really insane tricks. And there's been some material published on this. Dildog was one person who wrote some really cool stuff showing how to exploit WinINet DLL, which is loaded into memory for an Internet Information Server. And I think there's like one call, and it'll download a file from anywhere on the internet. So that's pretty cool. And it doesn't take very much room to code that. So anyways, there it is. Let's talk about exploits. What is an exploit? It's obviously a bug in software. Obviously, you all understand that there's a lot of bugs every single day being posted. Just look at USSR Labs, for instance. I don't think the guy ever sleeps. He's like 2 or 3 a day almost, right? Not quite that bad, but yeah. So Basically, there are people out there who just download software all day long and run automated scripts against them to find things like buffer overflows. And if you've ever done this yourself, you will suddenly be successful. You'll find a buffer overflow. I've downloaded stuff off of the net and found it within 10 minutes. So it's ridiculous. The code quality out there is terrible. So this is going to be a problem for a long time. The simplest form of buffer overflow is a stack-based overflow, but I'm also going to talk about heap-based overflows. Stack-based overflows, there's almost no excuse for them. If you have them in your software, it's because you're a bad coder. You need to learn how to not do that anymore. Stir copy needs to go away. And it's not actually the programmer's fault. You know, it's more, I think, libc's fault for giving me that function in the first place and makes me lazy and I just want to use it. So, okay, let's say I have an exploit and I run it against a box. What can happen? I can crash the machine. If I'm, I've never written a buffer overflow before and I'm going into a system, that's probably the first thing that's going to happen. I'm going to crash the machine or the application. Windows NT has exception handling and separated processes, so the best you can hope for is usually just to crash the process. So that's the most common type of result of an attack. Some programs have what's called exception handling. Does anybody here know what exception handling is? Okay. Basically, if I screw up something really bad, I can kill my thread, or I can crawl back on my stack and find some place that's not corrupted and just start there. So exception handling is really cool. Some people suffer from the illusion that exception handling somehow prevents stack-based overflows from working. That's simply not true. Where is the exception handler stored when you have exception handling? On the stack. So if I overflow my stack far enough, what's going to happen? I'm going to overwrite the exception handler. So that's actually making it easier for me to exploit it, actually, because I don't have to guess the return address. I just have to know that I overwrote the exception handler, and then I cause it EIP to jump anywhere I want, way over there, and it's going to cause and throw an exception, and then boom, my code's going to run. So exception handling is not a way to prevent buffer overflows. Mobile code, assuming it's a successful attack, mobile code can get into your system. Mobile code is a reality. Network worms are a reality. Viruses, obviously, have been around for a long time, but you don't seem to see a lot of worm stuff happening, but it's going on. File access, denial of service attack, these are all things that you are all familiar with, I'm sure. If you study bugs, if you go back through bug track, or say 8LGM or anything that's a really old list, and you just go back in time and look at all the bugs, you'll see that they keep repeating themselves over and over and over again. There's these classes of attacks that just keep working, and it seems like nobody's ever learning about how to fix it. My advice to you is, especially if you're an organization that does security consulting or architecture stuff, is make sure you do code review. And if you don't have the skills in-house to do that, farm it out to somebody else. Code is the key. I believe that things like firewalls will eventually go away because at some point in the future, these people are going to figure out how to write their applications, so we don't need to have firewalls in front of them. They're going to be secure natively. But so anyway, some of these classes are improper filtering. If you've ever looked at anything Rainforest Puppy's ever done, you can see him playing some pretty serious games with just content going in over an HTTP session. Bounds checking is what we're going to look at today. Bad authentication. If you watched the Firewall 1 talk earlier today, need I say more? And impersonation. Okay, so one of the main points I want to make in this first part is that how to get into a system is different than what you want to do once you're there. So there's actually two parts to a buffer overflow. The first part is what I call an injection vector, and it will depend on the machine you're attacking. The software version, whether it's Exchange, whether it's, some sort of RPC service, whatever it is, how I get my code in there is going to differ for each one of those situations. But the payload is not. I can have the same exact payload plug in like a little module to any of these injection vectors. So if I was a military organization, I would have a little group of goons over here programming all day for all the different versions of software that are out there that I want to attack. Then I have a separate group of goons over here making different payloads. Payloads to perform denial of service attacks, payloads to shut down entire subnets, payloads to install rootkits on boxes, payloads to make the ARP tables change on this box over here so that I can route ICMP redirect messages over there and cause that switch to stop working. All these things are possible with a payload. The cool part about this is that I can choose my payload depending on the effect that I want. I mean, it really is like a weapon. The payload is limited only by your imagination. I'm sure you guys can think of all kinds of cool stuff to do with one. So I think the next part of the talk is going to be about injection vectors, some of the things you'll deal with when you're trying to find those and exploit them. Injection vectors are very, very specific. If I change service packs on NT, an injection vector that worked yesterday might not work today. Different versions of servers, like if exchange, x.1 versus x.2, it's going to change perhaps. So it's dependent on your target, dependent on your operating system, depending on your application version. It's dependent on things like whether or not there's a content filter between me and the target. If there's a content filter in there that's stripping out certain characters, well, those are certain assembly language instructions I can no longer run. I mean, all I care about is that it's a hexadecimal value and it's going to be interpreted as something once it gets to the other side. The man is Caesar when it comes to figuring out ways to sneak through that kind of stuff. So it's protocol dependent and encoding dependent. The payload, as I just pointed out, is separate, but it still will depend on the architecture. Obviously, an x86 payload is not going to work on a Solaris box, well, excuse me, a Spark box. But there actually are ways to make a payload that will do both, but I'm not going to talk about that today. So a payload can be like a virus. It's just mobile code that gets in the system and does whatever it wants. So if you've ever seen a virus do anything, just know that a payload could probably do exactly the same thing. And once it's established on the machine, it can start spreading by any means. It can spread like a virus and just go on the files on your network, over your file shares, or on your local machine. Or it could be a little smarter and sniff passwords. Maybe it has a built-in version of SMB sniff, and it starts cracking hashes. That's obviously quite easy to do, as you've seen Lofcrack do it quite a lot. I could obviously just shut the machine down, denial of service, create a remote shell. This is the most common thing you've probably ever seen with buffer overflow, and it's probably because it's one of the most useful. Barnaby Jack wrote a great article in Frac 55 for basically writing one of these types of payloads for NT that would spawn a remote shell and give you access to it. Not using anything weird, not using Netcat. It just actually loaded up WinSock, bound all the right ports, and spawned cmd.exe and latched on to standard in, standard out. It was really an elite piece of work that he did there. So if you haven't seen that, you should definitely download Frac 55. Worm or a rootkit. If you want to get a rootkit, go to rootkit.com and download it. If I was a military organization or somebody who was really serious about taking down a site or a network, I would first do a scan and I would find out all the qualified hosts for every particular injection vector in my collection. So if all my goons over there have built about, let's say, 135 different injection vectors for 135 different qualified hosts, I could scan a network and maybe 10 of those injection vectors I could find work. And then I could match those up with the payloads that I want for the desired effect, and boom, we're off and running. I could hit one button and just spread. Injecting into a system, there's basically two types, content-based and buffer overflow. The key difference is that when you do a buffer overflow, the application loses control. Content-based attacks do not leave the process out of control. So that's the key. Process is in control. If I'm using content-based attacks, I'm telling the remote system to do things that it shouldn't do. I'm kind of bending its arm, but I'm not pulling its arms off. I'm telling it maybe to write to a file. And the only reason I can write to it is because some idiot at Microsoft forgot to change the access control list on the file during install. Buffer overflow is in a completely different situation. The process loses complete control. It's now running code that I put there. And I'll show you exactly how that works. I'll skip this one. Actually, yeah, I'm going to go through these slides. There's some reports that were released recently. Well, actually not recently, but they talk about who has been writing code. I'm trying to get to my slides here. Okay. If you don't believe that there are military organizations already doing this, then you're mistaken. There's actual reports released by the United States military that state that they are. The Cuban military, the Russian KGB. As early as '91, they have a report of them doing this. And then a couple of E&Y reports, just reviewing companies, asking them what's been going on, and they've all said, so about at least 50% of them have reported incidents of this occurring, viruses or other types of exploits being run against them. The one report by NCSA reports that it costs about $8,000 to recover from a single incident. That's an average cost. So obviously this is a pretty big deal, and it's costing corporations a lot of money. So everybody here heard of the Morris worm? Yeah, so it's probably the most famous worm ever. It shut down most of the internet, but the internet was pretty small back then, so it actually wasn't that many hosts. But it was really effective because there was the same software installed everywhere. It exploited a buffer overflow and in Finger D, I believe, and then something else in SendMail, and spread by both of those means. Well, today we also still have this situation. It's just a much larger scale. We have Wintel architecture with IIS, or take your pick, Apache. So if you take both of those together, you've probably covered most of the web server market. And it's all the same software running everywhere. So what happens when somebody, like remember when EI found that IIS hack? That was a pretty big deal. I mean, there was a huge portion of the internet that was vulnerable to that. If somebody had been on the ball, not released that to the public, and just done it on their own, they probably could have shut down most of the e-commerce sites on the net. They could have done a lot of damage. So we're putting our trust into some pretty crazy stuff, in my opinion, right now. I think people are suffering from illusions about how vulnerable they really are. In '89, there was another worm called Wank that hit NASA. It took 2 weeks to clean it up, and before it got out of there, it managed to spread to HEPNet, which is the High Energy Physics Net, DOE. So it got out of a gateway. Okay, so how do we get our payload into the system? There are a couple ways. Stack-based overflow is the most common. Heap-based overflow is much more difficult, but we've seen examples of it. We must control the value of the instruction pointer. That is the goal. So does everybody here know what an instruction pointer is? Okay, there's a processor obviously in your computer, and it keeps track of certain things using registers. And one of these registers points to the location in code memory that's currently being executed. And every time it executes an instruction, it increments by 1 or however many it takes to execute that instruction, and continues just walking along in the code memory. We want to change that to point to something that we controlled. We want to get some code into the system somewhere and make EIP, which is an instruction pointer under Intel, point to it. The challenges. Most importantly is size. If we have a very, very small size, we can't really do a whole lot. There's been plenty of buffer overflows which have been posted to BugTrack that had no actual corresponding exploit with them because they didn't have enough room to write one. However, you'd be amazed at what you can get away with just 100 bytes of memory. Most assembly instructions only take a couple bytes. If they have an address associated with them, maybe up to 5 or 6, but that's about it. So you can fit a lot of instructions in 100 bytes. If we're like I said, injection and payload is two different things, right? But if they're living in the same buffer, like I'm injecting them all within the same string, let's say, then they can't step on each other. That's another issue that we have to get around. And there's some ideas there. Another one is guessing offsets. Has anybody here heard of this, guessing the offset? It's because under certain conditions, you're not going to know where your code is in memory, so you have to guess where it is. That's really, really hard to do if you can't disassemble it. If you're sitting on a Linux box and you're running GDB, then guessing where it's going to go is pretty easy. But if you're from remote, it's very, very hard unless you run it and duplicate it in your laboratory. So there are some tricks to make this an easier process, and I'm going to talk about one of those. And then obviously null characters. Has everybody here heard of the problem with null characters in buffer overflow? Most of the time buffer overflow is going to happen because somebody didn't do a balance checking on something like a stir copy or an sprintf or something like that. Well, unfortunately or fortunately, these functions use a null character as a terminator. So if I have a null in my attack string, it's going to stop copying it, and I'm going to end up with 3/4 of a payload in there, and that's not going to work very well. So we have to get around the null character problem. Incidentally, that's not the only character that you can have problems with. I should actually mention this. I'm going to talk about null only, but there are plenty of other characters that can have problems, especially if you're going through a content filter. If you're sending a URL, there's certain characters which are invalid. If you're mime encoding your attack, there's only certain characters you can use. So, actually, some friends of mine this morning were telling me about some new ways to get around that. It's pretty cool. Actually, where's Barnaby? Didn't you tell me something this morning about where you inserted something and you needed a null, but it wasn't a null when you inserted it, but the program inserted and replaced nulls for you at each location for something like that?
And I needed the offset in the middle of my payload, and it actually replaced that character with a null, so I could jump to my code.
So it's kind of doing some of the work for you.
Yeah.
Okay, so does everybody here, does anybody here know how a stack overflow actually works? How, by overflowing the stack, I'm able to get to the instruction pointer to point something that it shouldn't? Nope. All right. The stack is doing a lot of stuff, okay? There's basically 3 areas of memory which are important in a process: the code memory, the heap memory, and the stack. And the stack is used for housekeeping. Every time a function is called, the stack is quote-unquote grown in size to support all the local automatic variables for this function, and things like where it was in memory, the last function that was called, all this weird housekeeping data is stored on the stack. So as I'm running around, I'm going to say I'm a process now. I'm a process, I'm running, and I'm doing this, now I'm going to do this, now I'm going to go over here and do this, now I'm doing this. Well, I'm done with this now, so I got to get back to where I was. How do I remember that that was where I was? It's because the stack tells me that, and I can go back all the way and do something else now. Well, we're going to cause that to not work anymore. The other thing is that if I have housekeeping on the data, on the stack, any data that I'm inserting in a buffer has to be able to overwrite it. So if my housekeeping data is over there, and my buffers are growing that way, I'm not going to be able to overwrite it. It's going to go the wrong direction. Fortunately for us, under Windows NT, Intel x86, and the way the stack works, buffers grow towards the housekeeping data. All right, so this is my cool little animated slide. My instruction pointer is pointing off to to code memory over here. So this means it's running some code over here. It's actually, there's a subroutine, okay? And we're running and stepping through it. And then I'm going to call another subroutine. So I take the current instruction pointer out of the register and put it on the stack. See how that works? Right there onto the stack. Now I'm going to do something in a new subroutine. So I'm actually making a call and I'm moving to somewhere else in code memory. So now I'm pointing to a new function. Well, that function needs room, okay? It has variables that are local to this subroutine that need to be handled. So those are allocated on the stack. So here's how it looks. We grow the stack, okay? Now we're going to play around, our subroutine's running, and it's going to be doing stuff up here in the stack memory. Okay, and when it's done, that's going to go away like that, and the IP is going to go back into there, and we'll be back at our previous subroutine. That's how it's supposed to work. Okay, so I make the call, IP goes on the stack, I jump to a new code location, allocate some more memory. It's not really allocating memory, we're just altering the value in the stack pointer, which is why actually it's very fast. So the stack pointer gets updated and now points to the top of the stack. That's it. So everybody kind of understand this? I can go on to the next slide. Okay, great. Stack overflow. Okay, so obviously the IP was pushed onto the stack. So I'm going to show that. Here's our stack, and I wrote some memory addresses here. This is what it would look like on NT. If you were on Linux, you would not see 00402014. You'd see something more like, oh, I don't know, BB something or 77 something. I don't play a whole lot on Linux, so, but I do know that it's a higher address. Okay, so I store my IP. And my stack grows up. Now, I have things that are going to happen up here. The subroutine is going to use this memory. Well, what happens if I'm filling a buffer? Let's say I'm storing 10 characters, but it doesn't do bounds checking. Well, the stack grows down, buffers, grow down when they're filled. So I'm filling a buffer. And if it doesn't get stopped, guess what it just did? Overwrote the housekeeping data.
Why is there an exit on that page?
A what?
Why is there an execute permission bit on the stack table, stack page?
That's a very good question. In fact, I believe there's some, the question was, why is there an execute bit on the stack page? Let me explain how this works a little bit. Remember I was talking about stack, heap, and code? Well, the computer keeps track of all these quote-unquote pages of memory. And it keeps, you know how files have read, write, and execute permissions? Well, so do pages of memory. And this fellow over here was pointing out that if the execute bit wasn't set on the stack page, would I be able to execute code? Does anybody know the answer to this question? No, you would not be able to execute code. Yeah.
That's actually not true.
Not.
If you execute code in stack, that's what I'm saying. For example, if you have the ability to modify a pointer, your code, which is elsewhere, you don't have to execute the code in the stack.
Oh, that's true. You do not have to execute the code in the stack.
You'd have to vector to something that was in the executable or a library, because your heap doesn't need execute permission either.
Well, if you're storing your code on the heap that wants to be executed, then you do have to have execute permission. I don't understand that then. If you could get the microphone so you could explain this.
The operating system loads the executable. It can load code and then clear the write bits on the code, give you heap pages which are only for data. Code won't be loaded in there, and those will not have execute permission bits set. Same for the stack. So you end up with all code loaded by a privileged operating system, all data that you can touch, not executable, all code not writable.
All right, so you're familiar with like these stack protection systems, executable stack patches and things like that?
This is something the operating system would do. Some of the StackGuard compilers do something to the compiled code rather than the operating system.
Right, okay. Okay, so I'm going to move on here. Okay, so everybody understands I can overwrite this housekeeping data, correct?
Question, was that part of the housekeeping part or?
This like pink area here I'm using to indicate that there's some housekeeping data stored there. It would be, for instance, the return address of the, so I can go back to the previous function that I was just executing.
I think I can explain why the stack is set executable. In older operating systems, it actually was not executable. Correct me if I'm wrong. Where's the switch? Correct me. Here we go. Correct me if I'm wrong. Some older operating systems had the stack non-executable, and that was changed to make the stack executable. And I believe the reason for the change was just a performance hit, that they had to check, the operating system had to check to make sure that memory that it was using was or was not executable, and the change was made for performance reasons, and I think now we're stuck.
Yeah, I'm not too sure about that, to be honest. I still am not actually convinced about that other argument you made, because when I was playing around with page tables, there is a bit which you can remove for execute, and you cannot load that into EIP. It will not execute, it'll throw an exception, it'll trap. So, but anyways, I'm not a god when it comes to protecting against this, so other people are probably a lot more technically advanced in the protection stuff. Okay, so the problem with null, I want to move on here and talk about this. The problem with the null character, obviously, is that if a null terminated string is passed through something like a stir copy, it's going to stop copying when it hits the null. So same diagram as before. I store my housekeeping data, and then my stack grows, and I start filling my buffer, which grows back towards the housekeeping data, and I hit a null character and it stops. So I didn't make it. I didn't make it to the null, or excuse me, to the housekeeping data. Obviously, then, the null must be past the housekeeping data. Store my return address, move up, go down, and boom. Everybody see how that works? Okay. Now I have to make a little trip and explain the difference between little and big endian. Has anybody here heard of this before? Obviously. On an Intel system, numbers are stored, in my opinion, backwards. So if I have an address that's 004010FF, it's going to be stored in memory as FF104000. Well, what's the last character in this then? It's a null, right? Well, if I want to inject that address and put it onto the stack, I could. And I'll show you this. Let's say that's our return address that we stored, and it has some value in it that's real and true and supposed to be used. We fill, here's our buffer going up. Okay, now we fill our buffer down. Put in, oh, that's a really crappy slide, sorry. It says 0C204000 if you can't read that. So the last number there is 00. Now, does everybody see how, still with a null character, I was able to put an address on there that was valid for the stack addressing range? Because it's little endian. Does that make sense? Okay, great. Injection is complete. We control the instruction pointer. Now the question is, what do we make it point to? How do we make it do something useful for us? There's the address. We saw that. Okay, so we have to have a payload. We have to put it somewhere in memory, so the most natural place to put it is in the buffer we just overflowed. So here's our stack again. We store our return address. We fill the buffer with our new address. There's our null. Does everybody see where the payload's going to go? It's going to go right into here. So we have a little room there to play, and we can put some instruction code in there. Does that make sense? Anybody not get that? Okay, because this is easy stuff. We'll get into the hard stuff later. One of the problems we might have here is that we might not have a lot of room. Let's say the buffer's really small. So that's one of the disadvantages to doing it this way. But this is the simplest way to do it. One of the problems is we have to guess an address, though. We have to put an address there at the bottom that we know will be on the stack. So there's certain tricks we can pull to make that easier to do. So with that confined payload, we might have to pull certain tricks, such as compressing our payload and then decompressing it somewhere else. Another one is to use only functions which have been preloaded into the process that we're exploiting. In a process, there's a whole bunch of functions which are already loaded. DLLs with exported functions that have been built into the import table. They're all out there in memory, just waiting for us to use them. There's no reason that we have to write our own code if the code's already there. We just need to jump to it. So if we use only preloaded functions, we reduce considerably the size of our payload. One of the things we don't have to do is build jump tables. I'm going to talk about jump tables in a little bit here. But the key is the usable functions must already be loaded. We can hard code the addresses, or we can scan for the functions through memory and then find the addresses. That's two ways. The hard-coded addresses are by far the easiest, but they're also the most prone to fail if there's something like a new version. A hard-coded address is not always guaranteed to work, because on some systems it may be there, and on some other systems it may not be in the same place. It might be 4 bytes over on the other way. And if we even get out of alignment by 1 byte, we're toast, because it starts executing entirely different things. It starts, the Intel processor will interpret it entirely differently. So we don't have to do that. We can use more stack if we want to. We're growing down the stack, and the stack, you know, it could be really deep, and we can just go as far as we want. So there's no reason just to stop right when we hit the housekeeping data. I can go right past it. I can start filling right past it. And does anybody here know what the problem would be with this particular situation? What's that? Well, if it works, okay, the question or the statement was it would throw an exception. It may throw an exception if I do it incorrectly. If I do it correctly, I'm still overriding the housekeeping data, but I need to override it with something else. We can't obviously have a null character in it, so we can't use anything with that 00. So we're going to have to pick a different address that doesn't have a 00. That means somewhere that's not the stack, if we're talking about Windows NT. So I'm going to show you some tricks there. Here I can have my null character, but it's way past the housekeeping data. I just can have no null in the address. Now, fortunately, most of the DLLs are mapped up into the 7.7 range under NT, which means we can easily use addresses up there. But all these little weird tricks have to be used to get back to the stack. We have to get back to the stack because that's where our payload is. Our payload isn't up there in the memory 777. Actually, you know what, my slide kind of sucks here because it says 77402008, but that's under NT, that would be incorrect. Our stack lives at 0040200 whatever. Okay, so understand we are on stack memory. That means we have a null character. So we have to pick a different address. But the advantage obviously is that first red rectangle up there would be like our return address. We can go all the way down the stack. We have all this room. We still overwrite that value there, but we just can't use a null. We do something that makes it return to our stack. Now, my stack diagram here is actually not accurate for NT, but it definitely makes the point. We wouldn't be jumping and moving back like this, but if we go down, now we can execute payload. See? Much more room than before. We're using the room after our return address. Does that make sense? So we have a lot of room here on the stack to play with if we want it. So under NT, when does address contain a null character? If it's on the stack, I call it a Hoglund address, and it means it has a 00 in front of it. We can use it, but it's going to like really reduce the size of our payload. A Hoglund address has no zeros in the address. I believe the stack under Linux is in Highland, so we don't have to worry about it, and we have an almost unlimited payload size at that point. Unlimited in the sense that we have enough to do pretty much what we want. So let's say we have a very large payload and our stack lives in lowland, like under NT, and we need to have obviously a large payload. So we can't use the null character, we have to do something tricky. So one of the tricks of writing a payload would be to use a CPU register. CPU registers often contain values and addresses which point to the stack. So in the next example, I'm going to show a register which is pointing to the stack. Let's say the D register is pointing to the stack. It was used for something recently. Maybe there was something stored there that we needed to, copy to, and so it's stored in this register. So what we want to do is make D become IP, right? That's the theory. So here's our stack. D is pointing somewhere. If we can overflow far enough to get to where D is pointing to, we can put our payload starting right there. But the key is we have to get D into IP somehow. And then we'll have a situation like this. See? We can make it jump right there. So that's right where our payload is going to start. The rest of it is inconsequential. We can fill it full of letter A. I don't know why, but hackers seem to be really fond of using capital letter A in their buffer overflows. There's actually a much cooler way to do that, though. If you don't use just the same letter and you're building a buffer overflow, you can pick a cycling set of letters like ABCD, ABCF, ABCZ, and you can make a pattern for it. And then when you actually own EIP and your program actually crashes, if you're the hacker playing with it on your computer, when you pop up, EIP will say, crash at address, 51525557, and all of a sudden you can find out exactly the offset of where you've owned EIP from. It's a useful trick and saves a lot of time. This book actually has some code in it that does that. Okay, so the idea is I got to get D into IP. So here's the trick. One of the tricks. Calling through a register. The following assembly and language instructions will translate to call EAX, call EBX, call ECX. Does anybody here know what happens when you do call EAX? What's that? It'll jump to the address in the register. That's pretty much true. It actually will first push the return address for the function it thinks you're in, and then it will jump to the register, through the register. But essentially, you can make it go to the address stored in the register, and that's the key point. It takes 2 bytes to do that. That's it. If I can find some place in memory that has FFD0, or in the case, what is it, FFD, is it FFD4, Barnaby, for EDX? It doesn't matter, everybody gets the point. So if I find these 2 bytes in memory, that's all I have to do is pick an address and put it into our housekeeping data that we're overriding. That address points to a location in memory that has FFD0, or with the equivalent. The cool thing about this is it doesn't have to be code memory. There doesn't actually have to be code that makes the call EAX out there. There just has to be somewhere data that has an FF and a D0 next to it. If I make EIP point to it, it'll think it's code. It could be in the data portion for all it cares. That's one way. Another way is to find a push somewhere, okay, and then find a return. Again, it's only 2 bytes. So if I find a 5-0, which is push EAX, and then later on I see a C3 that does a return, what that means is that EAX will be pushed onto the stack, and then later on a return will be called. As long as I know EAX is still on the top of the stack, when return is called, then it's going to get pulled off of the stack and get put into EIP. So I've just, through another method, obtained exactly the same thing. There's actually one more trick, which is not in my slides, but as the stack is growing and shrinking as we're running, sometimes the stack will have references to itself. Like there'll be a 00 address stored in the stack somewhere that references somewhere else on the stack. Maybe it was an argument from a previous function. Well, sometimes these can also be exploited. If I can find a whole bunch of pop instructions that will pop everything off the stack so I end up with the address that I want, and then a return, then I can return back into the stack. So it's yet another way to do it. That's also covered in this book. Okay, so if we jump to the wrong address, we're going to have problems. We're going to crash. Our payload certainly isn't going to execute. If we're guessing, then there are some tricks that will make our guessing easier. We can reduce the precision of our guess by using something called the no-op, which is hex 90. It's an instruction, which is fortunately 1 byte long, which means we don't have to worry about alignment issues. And we can fill an entire buffer with no-ops and call that a no-op sled. And I'll show a diagram of this. Here's my stack. I just called a function, so our stack grew up. Then we're going to fill a buffer, go down. There's our null. We overwrite this, but we also fill the last part of our buffer with no-ops. That's the cyan color there. So we're actually filling the buffer with no-ops. When we do this part right here, the no-ops are now there, okay? Here's the no-ops. So the no-ops are there. We overwrite the return address and jump somewhere, guessing, into the no-op zone. Well, we don't have to be perfect, because if we miss a little bit, as long as we hit somewhere in the no-ops, we're going to start sliding on the no-op sled. No-op, 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 no-op. We're going to start executing. No precision required. As long as we guess an address somewhere in that range, we then will execute through the no-ops until we hit the actual payload code. So if we hit a little less or a little more, it doesn't make any difference. That's the NOP sled. You'll see that used under Unix a lot more than you will under NT. We can store a payload somewhere other than the stack. This is useful. If we don't have any room on the stack, we have very, very little room, we can put just enough code on the stack to get to somewhere on the heap, and then store it in like an environment variable. Actually, that's on the stack. Somewhere like from a file, maybe we have HTTP headers that we pass, gets put on the heap somewhere. There's a lot of ways to get stuff onto the heap. Okay, so there's my buffer, and I make EIP point into the heap. That's pretty much it. There's other ways to exploit heap. You can actually overflow on the heap. This is not a stack overflow. This is an entirely different kind of overflow. It's called a heap overflow. What I just described to you in the previous slide was not a heap overflow. I was showing you that you can store your executable code out here just to make it easier for you if you don't have enough room on the stack. But we still overflowed the stack to get there. This is entirely different, a heap overflow. One example of this is when you have two C++ objects that are near one another. Does anybody here know what a VTable is? Virtual function table. Every C++ object that's instantiated in memory has to keep track of all of the virtual functions. The reason it does this is because of inheritance and polymorphism. The ability of, these are all C++ terms, but basically I can exploit things in the C++ language that allow me to override one function with another function if I've derived off of an object. That's all program speak, but in essence, what I'm saying is that every C++ object in memory has a little table of function pointers that point to code, okay? you can overwrite those, and they're stored on the heap. So this is our little V table. And any of the member functions, or excuse me, member variables stored within the C++ object are going to be stored beneath the V table, at least under NT. This is what I witnessed right here. And the member variables are just like the stack in that if there's a buffer there, they grow. But they grow away from the V table. So that's bad for us because we can't just make it grow right over the V table. But if two C++ objects are near each other in memory, does everybody see what's going to happen here? I can go over the V table of another guy. So once I've overwritten that V table, where do I make it point? Well, I make a new V table and I put it right in the buffer that I just overflowed and make it point in there. So all of a sudden I've changed one of the member functions in the C++ object. Does anybody know what a really good member function to change would be? It's in every object. The destructor. When I delete it, the destructor is going to get called, and the destructor is almost always virtual. You know this probably if you program at all in C++. So I make a new V table, and I spoof the addresses for all the functions that are supposed to be there. And when it's destroyed, my code executes. Okay, that was the first part of the talk. That was injection vector. Now we're going to talk about payload. Looks good. I'm doing good on time too. Okay. So there's a couple things we can do in the payload. We can use previously loaded functions. We can do things like encode our data in different ways and decode it and do things like that. Saving space or maybe making it look different, maybe even encrypting it. I think there's a guy, I think it's Luis, is going to do, he's going to do a talk at DEF CON about self-encrypting payloads. There's a lot of people talking about buffer overflows this year, I noticed. We can load new functions and new DLLs, and we can do things like obviously spawn a shell, and I talked about some of that earlier. Okay, so I don't remember what this animation is, so I'm going to run it first, and then I'm going to go back. Okay, yeah, this is like a diagram of what your payload might look like. Okay, so let me go back. The payload will usually start out with, let's say it's on the stack. Actually, it doesn't matter, it can be anywhere. You'll have a NOP sled, perhaps. Then you'll have real code doing real things, okay? And then at the end, you'll have this little block of data. Well, it's not code, it's data. And it's there because when I do things with real code, I oftentimes need to pass arguments to functions. Many times these arguments need to be encoded somewhere. They might even be ASCII strings. And you know, if my ASCII string might be, you know, http // cult of the dead cow /bin / exploit code.zip or something. So that all needs to be stored somewhere, and it's going to be down in that red area there, down in here. Okay. In order to reference all that data that I have in the data section, I have to know where I am in memory. So this is the first trick in the payload. I could be anywhere, okay, and I don't know where it is. So my assembly language needs to do something to help me figure out where I am. Well, the cool thing about it is if I call call, okay, the assembly language call, it is going to push the instruction pointer onto the stack. Well, once it's on the stack, I can get to it. You can't just load the instruction pointer out of the register, it doesn't work. But you can do call, have it pushed onto the stack, and then you can pop it. And you can put it somewhere. In this particular case, I'm putting it into EDI, which is just a register. Actually, you know, and this is a good time to bring this up. This particular trick would not work because call reloc and then reloc being beneath it like this with pop EDI would translate to something like E800000000. There's four null characters in that. We can't have that. Does anybody know how you might change this call? Actually, whoever can figure this out gets a copy of this book. How could I change this call so there's no null characters encoded into it? Once again, the call instruction will translate to E8 or something close to that and then 4 zeros because I'm calling forward 0 bytes and it needs to store the address. What's that? Okay, XOR the bytes. How could I XOR the bytes and un-XOR the bytes if I don't know how to... Oh, well, explain to me better what you mean, actually. How would you do it, specifically?
Damn it, pressure. Let's say you want to store like a null address on there, then you could just XOR that with ones or something before you get to it, or have, I guess you'd have, what? If you store like 255, 255, 255, 255 on the stack, and XOR that again, you'll get 4 zeros. If you XOR it with itself, you get 4 zeros out of that.
How would I make, how would I point to it so that I could run XOR against it?
Excuse me?
How would I point to the memory that I want to XOR?
I guess you'd have to guess via offsets and OPSLED or hard code and address.
Yeah, that might work. But I don't know where I am in memory.
I don't know, but I mean, could you jump and then do reloc as -1?
Woohoo!
Frec 55 rules, by the way.
UPC route.
Technical assistance, please. Screensaver? Hopefully. Oh, good. Once again, thank you, Eli. Okay, so the correct answer to that question was you can do a call in reverse. And a call -1 will translate to E8 and FF. There's no nulls in that. Good. Very, very good. Okay, so that's another way to do the same thing. Once we know where we are, that means we have a register somewhere now that points to our location. We can now offset from that register to get to all the data stored in the previous slide, all the data stored in the data portion. So when we actually do the call and then the pop, we're going to find out this location right here, okay? And now we can always reference off of that address to get down to the data. We know where everything is now. Okay, now the XOR protection. My ASCII strings are probably going to have to be null terminated, or they may have zeros in them, or maybe I'm storing other things that have just numbers or something that have zeros in them. So we can't have any nulls in our data portion either, otherwise we're going to cut it off prematurely. So we just XOR every single byte with some value, and now we have this XOR encoded payload, or excuse me, data section. When we're done, we just XOR it again to decode it. So we send it XORed. When we actually inject it, it's already been XORed. We XORed it locally and stored it locally that way. We run it against the remote system, and our payload's actually going to decode it for us. So there's our NOP sled. We begin decoding right off the bat. Right after we figure out where we are with the getting bearings, we then begin using that address to offset to the data and begin decoding it. And we unencode all the XOR, all the data. Okay, so once I've done that, I can start using function calls, which are already, I can hard code function calls. I can do, call 77F700 or 011B or something like that, and it would work. It would actually jump to that address and run it. So all the little pink regions I have out here are out in code memory. This is code memory, and these are all different functions. They're just located wherever they're located. And as I run, I can just call them. And then later on, I might need another one, so I call it. And then later on, and so forth. That's the easiest way to do this. Of course, the problem is we don't always know where these guys are going to be, right? So we need a new trick. Okay, so the pro to this is it makes code smaller. But the con is obviously if it's not in the same place. This is a problem if we have dynamically loaded DLLs, for instance. There is one side effect, though, or there's one other thing I have to mention. Some DLLs are usually in the right place. Can anybody here, this is another good one. Anybody tell me which DLL is almost always in the same place under Windows NT? Too many people answered. I'm not even going to go there with that. Okay, we'll try again later. That's pretty bad, wasn't it? Okay, so let's say I don't have the functions loaded into memory. Fortunately, there's always two functions available to me in any process: load library and get proc address. Load library allows me to load any DLL, and get proc address allows me to load any function address out of a previously loaded DLL. Get proc address allows me to specify the name of the function in ASCII that I want to use. So obviously I can store those names in the data portion. I can load any DLL I want and then find any function in that DLL. That's really handy. I mean, it's almost limitless now what I can do. There's plenty of DLLs on the system which do a lot for me. So I can store the function name down in the data portion. Let's say that, hold on, let me find out what this slide is doing. Okay, get proc address is already loaded, so I call it, okay? And I pass it the name of the new DLL that I want, or excuse me, in this slide, we'll say the DLL is already loaded. This is slightly misleading. We'll say the DLL is not loaded, and it says load DLL by name at the top of that slide. Does everybody see that? Load DLL by name? We're using load library here. Pretend like get proc address says load library. Okay, so I call load library and I give it the name of what I want, and it suddenly appears in memory. I can then use get proc address after I've done that to do the same thing. Get proc address, give it the name of the function I want. Once again, that's stored in the data portion, and it gives me the function address. So then I take that function address and I store it somewhere where I can use it, and that's called building a jump table. So I get proc address, store it, get proc address, store it, get proc address, store it for every single function that I need to use. And I can just put it right into my data portion. Once that's loaded, I can begin using those functions. Boom, and I'd use it. I have to call through the jump table. So I actually call jump table and it jumps to the function I want. Everybody see how that works? It's pretty easy. So I'll have one entry in my jump table for every single new function I need to use. Okay, so to do this, I have to store the ASCII name of every single function I want to use. Okay. Jeff just alerted me that the reception is starting shortly. If I'm completely boring you, get out of here. But I'm going to keep going, so hopefully you... Otherwise, you can keep going all night. Yeah, I'll just keep rambling. But I have 2 more books to give away, and if I pull another one like I did before, you might get it. I'm going to have to watch my screen before I make that mistake again. Okay, so in order to do that, obviously, we got another one down. Okay, obviously to do that, I've got to store the ASCII name of every single function I want to load. That's going to take up a lot of room, right? Especially if there's a lot of them. Especially if I'm storing the names of DLLs and functions. Obviously, it's going to take up a lot of room. So hackers have developed this really cool technique called hash loading. Hash loading works like this. Instead of storing the ASCII name of the function or DLL I want to load, I store a 4-byte hash of that name. The chance of a hash collision is almost next to nothing, so all I need to do is store 4 bytes and then go out and find and hash everything that's in memory to find that string. So basically the hash is equivalent to the string as far as I'm concerned. I can reduce the size of my data portion considerably. I'll show that in the next slide. We can find any function we want and we can load any DLLs just like before. Okay, does everybody know what a PE executable is? Portable executable format. Every single binary under Windows NT is stored, well, not every single one, but most of them are stored in this format called PE. Well, in the PE header is stored an import table. And in this import table are the names of all the functions that are currently loaded. In some cases, they're loaded by ordinal, and that would change the situation slightly, but most of the time, I've seen them loaded by name. And in this case, we're going to exploit that. Inside of the PE header is an offset, which points to another part of the header, and then inside of that part, there's an ASCII name and a corresponding address. It's telling me that this function, by this name, runs or exists in memory at that address. It's already there for me, and it's already loaded into memory. So I check my CRCs. Obviously, my data portion is no longer storing ASCII text. Now it's storing CRCs, storing 4-byte values. So I take one CRC and load it up, maybe into a register or something. And then I go into the PE header, and I find an ASCII name. I hash it again. The payload does. The payload runs a hash and compares it against the CRC that I want. If it matches, it takes the function address and drops it right over the top of the hash. The hash is gone now. The previous hash, the one I just used, is gone. But it's convenient because I have basically 4 bytes for every single function I want to load being replaced by 4 bytes for every function address. So it's nice and clean. As I go along, here we are, boom, load, boom, load, boom, load. See how that is? It's nice and clean. No ASCII text. If we had, this is an interesting slide. If we had a really, really confined payload space, we can do really wacky stuff like compress 2 assembly language instructions into a single byte. I've seen a guy, his name is Jeremy Koth, I think. He published something on BugTrack that did this. It was a long time ago. You could double the capacity of your payload, but it also seriously decreases the number of instructions you can use. You could also be confined by a limited character set. Let's say your URL encoding or MIME encoding, your payload is obviously being filtered somehow. Caesar's Challenge 2 years ago, Caesar's Challenge is a party which happens at DEF CON, and there's a challenge posted to the hackers who arrive, and they have to solve it by the end of the night. Caesar's Challenge that year was to make a payload that would work through a MIME encoder. Well, a MIME encoder only allows certain certain characters to be used, which limited the instruction set considerably, down to a bunch of short jumps, or a short jump, a push, a pop, and a subtract. Well, what we were able to do with this is load up into, well, actually, we would push a value onto the stack, then we'd pop it into a register, and then subtract that register until it was the actual instruction we wanted, and we'd push it back onto the stack. And we just keep doing that over and over and over again. It worked. Also in the same challenge, since we didn't have jump, we couldn't jump to our portion on the stack that we were writing to. So we actually had this thing called the backwards bridge. We didn't want to use jump, so instead, here's our payloads running along. So it's doing, load, sub, push, load, sub, push, and so forth. Meanwhile, it's pushing those down here, and they're growing up towards us, okay? So as we go down, we're also filling up. And we calculated the size exactly so that when we were done in decoding this, we just ran right into our real code and began executing. That was the backwards bridge. The source code to this is available on caesarschallenge.org. Okay, so one of the other things we might want to do is load a new DLL. Let's say that there's no DLLs in memory. I already kind of covered this. I guess I didn't think I had this slide, but we have a DLL. We call a load library. We give it the ASCII name, and it actually adds a bunch of stuff to the thing. A good DLL to load is WinINet. Dildog talked about this in his DAO of Windows Buffer Overflow paper. It provides these really cool functions like internet open URL and internet read file, where I just give it like a URL address and it goes and downloads it for me. It does all the work for me. Why work? Why sweat? My payload is really small because I only have to make 1 or 2 function calls, and it'll download the file. Then all I have to do is execute it. The other cool thing about it is I could, if I was a hacker, I could go out, an evil hacker, I should say, I'd go out and place it somewhere on an anonymous website where nobody could find it, or excuse me, nobody could trace me to that site. If you were an admin and you saw this go out and this file get downloaded, you could go out maybe and find this page somewhere on GeoCities, but you'd never catch the guy that put it there. So it's anonymous, basically. Another good function to load, or excuse me, DLL to load is the WinSock DLL, obviously. And Barnaby's article in Frac55 did just that, and it used it to open a socket. Another way to make function calls is not actually use DLLs at all. It's to make interrupt calls. It's an entirely different way to make something happen. Okay, now this is one I know it's not on the slide. Curl 32, right? Which DLL, actually which interrupt call, what's the interrupt number? No, excuse me. That's on the slide. You're not getting me that easy. Which DLL does kernel 32 wrap in order to make these interrupt calls? Somebody has to raise their hand or something, because I don't know who it was, so nobody gets a book.
Okay, we don't need one.
Okay. Actually, next time I do that, Eli, you got to go with the microphone and pick somebody. Keep it all nice and orderly. Okay, so an interrupt call is really easy. All I have to do is load a register with a number, and then load another register with a pointer to basically the arguments for the system call, and then I call an interrupt. An interrupt is usually encoded as 2 bytes. And I have 2 examples of that, one for interrupt 2E and one for interrupt 80. I believe interrupt 80 is there because it's the system call under Linux, and 2E would be the same equivalent under NT. Referencing Barnaby again, I think he used about 5 functions to attach those named pipes to each other, execute CMD, and then make those WinSocks. I'm going to use the WinSock library. I could spawn a process with interrupt 80 under Linux. That's pretty easy. I could spawn a process under Windows NT with 1 call, a create process. Worms, I'm not really going to go into this because I'm already over time, but obviously a worm, once it's established, can exploit trust relationships to get wherever it wants to go. Lysine deficiency, really quick. If you have a worm and you're programming it and you're testing it, you don't want it to get out of control and take off, right? So we came up with this idea called lysine deficiency. Basically make some rule, like a floppy has to be in the drive or a file has to exist, and if that isn't the case, it doesn't spread. That's the way you can keep it in your laboratory and make sure it'll never get out. And Caesar wrote some interesting stuff on this, and it's posted on the rootkit site. So I think it's just, it's a good idea to have this lysine deficiency, and obviously it was a complete ripoff from the dinosaur movie. Okay, so recap. The injection is not the same as the payload. Payloads can perform a variety of things. Now, a service attack, they can be a worm, remote shell, rootkit. There's many, many, many challenges with injection. Null, obviously, stack size, different character encodings, Highland Lowland address. You have to be able to get to the stack or wherever your code is being stored. So there's things like calling through CPU registers as tricks. I've shown you that a limited opcode set can still be used to build a fully functional program. Our payload has to be encoded. We can build jump tables, we can load any DLL in the system, find functions, we can hardcode the addresses, saving space, or we can load them dynamically, and we can use lysine deficiency to keep our worms from spreading uncontrolled. Thank you very much.
Good.